So after having looked at the protocols of layer 3, IP version 4, IP version 6, and all these helper protocols, I will now focus on one of the major tasks of the network layer, routing. Basically, how does a packet find its way through the big worldwide network? First of all, I will introduce some concepts, and then I will focus on concrete examples, OSPF and BGP. So, what are the most commonly deployed routing principles? We have to look a bit into the theory to answer, well, actually, how do the packets find their way through the network? I mean, it's a network of millions of nodes. So how do we find an optimal path? So what is the best path? We'll see we have different metrics for this. What is best? What is the optimum? And we will also learn how to organize this worldwide routing. We learn to distinguish between a so-called intra-domain routing and an inter-domain routing. Maybe remember domains, autonomous systems, organizations handling their networks in a certain way. I will come back to this. So what is the main component? It's a router. So in a very simple form, a router accepts packets from whoever, third parties, and forwards them. And somehow all the routers, they have to be coordinated, and routers can be explicit machines in the internet, so real, expensive, big devices, but routers that could be any host, so you can simply use special routing software. So what is the idea used in the internet? We have a so-called hop-by-hop-based forwarding. And this forwarding always goes towards a certain destination. So for example, on the left-hand side, you see your computer and you want to click on one of the videos I produced here. Then typically it goes to your DSL router. Then it goes to one of the routers of your service provider. Then maybe 2, 3, 4 more routers before you then finally reach one of the servers of YouTube. Looks simple, but what happens if you have alternative paths? So in this example, yes, the packet could take this very straightforward path towards YouTube, but it could also, for whatever reasons, take a detour. What are reasons? Maybe someone cut the wire, could be a reason. Or this path is too expensive. Or you don't like some provider of a network. Or you have secret data and you don't want to have the secret data following a path through a hostile country, whatever. We will come back to these issues. Okay, so what do the routers need to perform this forwarding? Because each of the routers here, they have to decide when a packet comes in, okay, does the packet go this way or that way? We will see that this decision has to be done within nanoseconds, very, 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 very fast, because we have many packets per second. And then additionally, all those routers have to cooperate in some distributed fashion to create these routing paths for all the packets. This doesn't have to be done in nanoseconds, so this is rather a task of milliseconds or seconds. So we'll see that all the routers, they contain two data structures, two tables. One, on the right-hand side, that's the forwarding table. This is when I talk about nanoseconds, so it doesn't matter if it's some nanoseconds, many nanoseconds, so this has to be very fast. A forwarding table basically tells you, okay, now a packet arrives, what is the output port? This decision has to be made very fast. On the left-hand side, we see a so-called routing table. In a routing table, let's say this is rather, we update this and fill this table seconds, milliseconds, that doesn't matter. So, but orders of magnitude slower. Routing tables, there you will find the list for all possible destination networks or all the networks the router know, and then possible choices for next hops. For example, you will find for this network, you have two choices. So you can go via router 3 or router 4. So routing table can have choices. So different paths of what can be the next hop. There might be also some meta information, path length, maybe cost or data rates or whatever. In the forwarding table, you don't have these choices. You see, okay, if a packet with this certain network prefix reaches the router, this is the next hop. So there are slight differences between routing tables and forwarding tables. So routing tables, they answer the question, which paths can we use to fill our forwarding table? So the router can select a certain path based on certain criteria. The forwarding table is then used to which destination network do we really forward the packet. And typically forwarding tables or parts of are realized in hardware, and the routing table, well, memory, hardware, software, it's not that time critical. The routing table is filled with the help of routing algorithm and routing protocols, as we will learn. And then the router picks from the routing table certain, selection and fills the forwarding table. The forwarding tables, they can be stored, for example, on specialized memory on the network adapters. Okay, I will come back several times to this routing and forwarding and what the difference is, but you should learn the difference between routing and forwarding. So what is the overall question? So, if I receive a packet as a router, to which destination network do I send it? I mean, there's this IP address. And now, one idea could be to compare the IP address with a huge database containing all IP addresses of the planet. But quite obviously, that doesn't work. So what is done is I compare the destination IP address with all the entries and find the entry that overlaps most with the destination IP address. As I mentioned several times, the routers only store certain network prefixes. Routers never store final IP addresses that include the host identification. There are millions of them. So even the big backbone routers, they contain maybe 500, 600, 700,000 entries, but not millions. Okay, the idea here is we use the so-called longest common prefix match. How does it work? So longest common prefix. So we store prefixes, and now we have to find, using the destination IP address, which is a full global unique IP address, and then we have to find a match with the longest common prefix. So, example, we have a certain destination address on the right-hand side, 172.217.2078, and excuse me for still using IP version 4, although I always say please use version 6, but here it's a bit simpler to understand and simpler to write. So we have the forwarding table as shown in this example here on the left-hand side. So where does it basically match? We see from the destination address 172.217. Okay, that matches with all three entries as we see so far, but we want to go for the longest common prefix match. So what we do is we basically compare. So we compare the destination address with these entries. Then we will find out that, here it doesn't even match. So we cannot simply say, the first two bytes match. No, we compare, that doesn't even match. Okay. So what else do we see? Oh, we still have two candidates. Why? If we perform this AND operation, both candidates, they work. Look at the network mask here. This network prefix, 172.217, matches. We see this here as well. And for the other, it also matches. Well, okay, here in this example, even 3-byte matches. And you can already imagine which one is the longer common prefix. It's the upper one, shown here in green. So 172.217.20, that's the longest in this case, common prefix match. So we have one not matching, we have two matching, but we have one that is longer matching. So longest common prefix, that's the idea. This is why in this example, we pick this router for forwarding with the appropriate port. Okay, so what happens now if an arbitrary packet reaches the router? You see here a destination address where you will not find any matching prefix. None of the prefixes here match. This is why we always have a default entry. So if no entry fits, the router selects the default route. And then the hope is that maybe the next router knows what to do. So a router doesn't store all the end system IP addresses, but also doesn't store all the network prefixes. That's not necessary. So routers only store a certain part of the network prefixes, and if they don't know what to do, they have a default route. So that's the idea. Okay, so routing and forwarding, those two parts. Here we talk about forwarding. Forwarding is based on the longest common prefix match. Now, again back, what about the routing? So which path to select? The forwarding, we've seen, that's this prefix matching, fast, nanoseconds, very fast. Now the routing, which path to select, well, this really depends on the application. As I said, if this is a top secret, whatever communication, you might not want to forward this data across an enemy country. Or if this is delay sensitive stuff, then you have maybe to take another path compared to mass data download, where cost, whatever efficient download is important. So it depends in the end on the application scenario which path is best. Sure, if the internet doesn't know the application scenario, then it will try its best depending on the settings of the routers, but maybe this path is not the best for a specific application. So the optimum path really depends on the application. You cannot say this is always the best path. Okay, so there are legal issues, data rate issues, cost, load balancing issues, etc. We'll come back to this. So forwarding, the fast one, that's the longest prefix match. The routing table, well, collecting different possible paths. Okay, so now, coming to some scenarios that will explain some more details. First scenario, very simple. We talk about intra-domain routing. Why is this simple? Well, the routers here in this cloud, they belong to the same administrative domain. Why is this simple? Well, because then whoever organizes this cloud can then decide what is a best path. So then, depending on, well, certain goals of the operators, to make money, to balance load, to whatever, you can then actually run a certain policy. What are good paths? How do I create a path? So what are the criteria, etc. Okay, so you see in this example, the routing table shown here in router R2. And as you see, certain networks, so if you go, for example, in the direction of 20, then you see, okay, it goes via router 3. So this is this, as you see, 172 to 1720. That's the preferred, if I say, for example, the preferred route. But you also see that there's an alternative one that goes via router 4R4. So that's also 427 to 17.20. So you see two possible paths to reach this network with the prefix 172 to 1720. Okay, so this is what you can write in our routing tables. And then the idea here is that the operators then can determine on their own how to weight these different paths to say, okay, we have here, let's say, with a higher priority for this network prefix, we take the upper path, for example. And for another network, as you see, we have choices. So we can pick, now for this 23, we can pick either path. You see, the 23 can take the upper path, and with the same, let's call it a weight now, can take the lower path. Okay? That's up to the administrator of this domain. And then we can pick two candidates here, take them into the forwarding table, say, okay, if a packet arrives, for example, we take those two green ones and this green one in our forwarding table and say, okay, this is then the path to take. You see, for this network with the 23, we can pick either. Well, that's up to the operator. So that's for intra-domain. So you can choose your policy, whatever you like. But for inter-domain routing, way more difficult. You have many different network operators, and they have a different understanding what is a best path. So maybe there's an operator that wants to centralize everything, to monitor traffic. There's an operator that wants to decentralize, whatever. Maybe there are operators that prefer this link before they take another link. Some of them go rather via fiber or wireless or whatever. Some are more expensive, some are cheaper. So let's have a look at this example. Again, if we now assume we have three different operators, what we perform here is an inter-domain routing. The routers belong to different domains. Then it could be the case that, now assuming a very simple scheme, let's always take the cheapest path. Then most likely the traffic coming in, no matter what the destination is, all traffic will take this cheap path, and from this one maybe this one, and then it goes up to YouTube or to the right to Google. And you will most likely not take this more expensive one if money is the metric. But what happens if the country here is a country you don't like? So maybe this is very, 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 very cheap, but for certain reasons. And you don't like your traffic taking this path, because this might be your enemy. And you say, they do eavesdrop. They listen to the traffic and they learn too much by listening to the traffic. Then you would say, oh no, I, for a certain type of traffic, will rather pay the price and go here. Okay, but now this is your individual policy, because maybe there's traffic coming from yet another domain, and those two domains, they are friends. So, and they have no problem if their traffic takes the cheapest route. Whoa. So you see, it's getting complicated. So you may have really completely different policies. So inter-domain routing requires a path selection based on individual policies, and they can be really different between different operators. And we will even use different protocols that support these policies versus, as you would imagine, first thought would be, well, take the shortest path. As you know from theoretical computer science, we know how to calculate the shortest path. Well, in this case, the shortest path is not always the best one, or not even a path you can use. Okay, basic concepts. So first of all, you should know, what does it mean? Longest common prefix match. Where do we use it? Why do we use it? Then you should have also learned the difference between routing tables and forwarding tables. What makes them different? And then also, what are fundamental differences between intra and inter-domain routing? I will come back to this when we look into the protocol, but for now, what are the fundamental differences?